Go. Hello, Miss Area, right? Okay, so we're given this graph, right? This is the weighted graph, right? Weighted graph. Graph is the collection of vertices and edges, right? Yeah. A tree is also a graph, right? Yeah. Tree is a graph. It directed acyclic graph, right? Directed, from the parents to the kids. Acyclic means it doesn't have cycles graph. This is the graph, weighted graph. Okay. We can have the weighted graph with direction. Okay. So look, we can have this direction. Yeah. Or we don't, right? It doesn't matter. So here, if this is the weighted directed graph, right? Weighted directed graph, WDG, and we want to find the shortest path from the S to E, right? The accumulate cost, right? So which one is the shortest one? Can you see very clear?
S A D C F E.
Well done. Look here, one. Don't fall for that because this is a trap, right? It asks you to go this, but look, there's 100, much bigger weight here. But our humans are quite clever, right? We can see this like instinct refract, and okay, so this is not the ideal way. So with the depth of search, okay, that's okay. With the depth of search, it doesn't work quite well in this case because the depth of search doesn't handle the cases when the edges have the cost, right? Yeah. And the breadth of search either, right? The breadth of search isn't working quite well as well, right? So now today we're going to talk about another search which is called uniform cost search. This is very good to handle the shortest path from two vertices. We have actually talked about another algorithm called Freud. You probably can't remember Freud. It's the ON cubic search. Look. Yeah. Look. Why is that? Look. It's actually based on the dynamic programming. Look. It's like that. Okay. The shortest distance between I to J is equals to the mean. Mean of what? Mean of shortest distance. Dij, and then dik, and then to d plus dkj. Okay, what does it mean? Actually, it's very easy. Look here. I want to calculate the shortest distance between I to j, right? Yeah. Then I can loop this. I put it in the loop on 3 times, and then what happened? So if I find a path. Look, if I find a path somewhere, this is k. Alright. If I find a path, I want to calculate the shortest distance between I to j. But now I found a better, shorter path, which is ik plus ikj. Then I can replace ij with this part, right? Yeah? For example, this is 100, and this is 1, this is 2. So dij is 100 now, but I found dik is 1, dkj is 2. So I can replace the ik with 1 plus 2 equals 3. Yeah, that's about it. So we just do this for k in range n, for I in range n, for j in range n, and then do this dij equals mean dij, comma dik plus dkj. That's it. Well, this is the simple shortest path between any 2 points, any 2 vertices, right? But it takes time. It takes ON cubic, that's slow. That's why we're not talking about that today. We're talking about the uniform cost search. So the way to understand uniform cost search is actually very simple. For the breadth of search, we use the queue, right? First in, first out, right? But for the uniform cost search, we replace the queue with the priority queue. Okay, that's the first thing, priority. First in, priority out, right? Yeah. So the people are waiting in the. So priority queue is like that. Okay, so you first in, first out, yeah, first in, first out. Now, it's not like that. So you have let's say who is taller gets served first, okay? So I have a people here, yeah, this is a people, play in the queue, and then here, a John, taller, and then another guy, John, much taller. Okay, so now, yeah, if the most higher priority is the higher priority, then when we DQ, then this guy gets front of the queue and get served. Okay, this is called priority, right?
He wrote
Yeah.
that.
Yeah. Okay. So now, so first of, if the cost is all one, can you imagine what happened? If cost is all become all one, what happened?
It'll be like.
It will be like what? What did I just say? We are trying to replace the breakfast.
Research.
Yeah, exactly. We're replacing the breakfast search with the priority queue, right? But if the cost is all one, all the same, all one, okay? Then it actually becomes a breakfast search, right? So how can we do this? Look, if at the beginning we put a S in it, so S in it, okay? So S, the cost from S to S is 0. Now we take the priority, the high priority, which is the lower cost from the queue. I remove it, I put it in S, okay? When the removed vertex is the destination that we quit, we stop the algorithm because we already found it, okay? Now S is not E, so we continue. So S0, so S can go to A, right, with the cost 2. This is the only way it can go through. So I put the A, which is 2, right? Okay, so now the next one I want to take it out is only one element. So I take it out, A is 2. I put the A in the visit set. From A, I can go to D, C, B. Then I can include all the children. So, okay, so A to D will be 2 plus 4, accumulate cost, yeah? So it will be 6. And SAB, it will be 2 plus 3 is what? Is 5. And then EC will be 2 plus 7 will be 9, okay? Yeah? Okay, and now I continue because I haven't found a destination yet. So now D is 6, 6B is 5. I take the 5, yeah? Because 5 is the lowest cost, which is the higher priority. I take it out. It's not E. I continue. I put a B here. B is 5. From B, I can go nowhere. So I stop. I just don't append any kids. Then now next one, D and C, which I should take D because the cost C. I take a D.
6.
D. I put it here. 6 plus 2 is A. Yeah.
Yes.
D. If there's a 2 direction, we still not going back to A because A is already visited, so we don't go back. Yeah. Okay. So C is A. And then we for the next round we take C equals A, right? Yeah, put it here. C equals A, and go to F and G. A plus A, F is 16, right? G will be A plus 1 will be 9, right? G, okay, 9. Yeah. So for the next round, I take a C, but it's already in the visited, so I continue. I skip it. Yeah. Look here. Yeah, so I take this, I skip it. Now, F and G, which I take a G, right? Yeah, I take a G, I put it in here. G will go to E, will be 100. E will be 100, right? Okay, now, F16, E 100. Is it? No. What G, what's the, actually the cost is not 100. G, is it 100? No? It's SA 2421. 2421 is 9. 109. Okay, sorry. And F, I take a F, right? F16. I put it here. So 16 plus 2 will be 18. So E will be 18. Right? Look. So 18. Now the next thing, look, I take a E, which is 18, right? Okay, now because I do the removed vertex is E, is the destination, and I stop the algorithm, which is 18. Is 18. 2, 4, 2, that's 8. 16, 18. Yeah, that's about it. Okay? Yeah, that's the uniform cost search. It's actually quite easy to understand if you think about breakfast search. The only difference is that we are using the priority queue, right? The uniform cost search does not care how many paths, right? It only cares is about the accumulate path cost, right? You always pick the smallest, the highest priority, okay? So let's quickly write the pseudocode, okay? A little bit. Okay. define, let's say we have a shortest path. And then the shortest path of a graph, in a graph, let's define it as, there are a few ways to define the graph, which we can give in edges, as a list of edges, okay? So let's give in the edges. And then we have a star, edges, star and end, right? So now G, the graph will be default dictionary. Default dictionary is, we're using the adjacent list to store the graph list. And then for each edges, it will be given as from, to, and weight. Okay, so for A to B, we have a cost in edges. Now we can do this GA. Okay, plus equal. Let's plus as B, the other vertex of the edge and the cost. Okay, now we have stored the graph. We have processed the edges and put it in the graph. Okay, now at the beginning Q is a priority Q, right? So at the beginning it only contains the from the star, which is let's say cost 0 and start with the S, right? Cost 0. Yeah, we put the S in the Q, and the cost from S to S is 0. Yeah. Okay, and then wire Q. Look, this is quite similar to BFS. And now what happened? We also need to store a scene, yeah, a half set to remember the set we have, remember the vertex we have visited. Okay. Now wire Q, and then we have a current. We have a current cost. The current cost and the current will be equals the. It's not Q top left, right? It's for the priority Q we use the hip hop. Remember hip hop Q, right? And then now look, if the current equals the distance, equals the destination, then we return the distance, we return the cost, right? Yeah. Then the next thing is to do what? Then we need to check if the current is already being visited, seen. Then we just continue, yeah. We just skip this one, and then now the next thing is go through the neighbors of the current, right? So for n in G current, okay. G current is actually the containing a tuples, array of tuples, which is the vertex and the cost. So we need to do this as n is the vertex, C is the cost from the current to the end. So now we just need to push this into the priority queue. Hip hop push Q, and then D plus C, okay, D, because current cost is D and the new cost is C. So the new updated accumulated cost is D plus C, and then the vertex is N, right? And then if we can't visit everything, the destination here, we return anything. We return none or return -1. Doesn't matter. Okay. Look at this template. Can you see the difference between this and the breadth search? Can you point it out?
Hip hop.
Where is that? Hip hop. Yeah. With the breadth search, we use what? Q dot. Top left, exactly. And then another difference. With the hip hop, what's the other to push it?
Pen.
So here is different, right? So in the breadth search, it will be Q dot append, right? So this one is picking the lowest and the highest priority, which is the lowest cost, right? And here is to pushing the kids of the vertex into it, and all other things are quite similar. Okay, so this is the uniform cost search. Okay, so it's quite useful to find the shortest path between in a graph with the weighted, It could be directed or directed graph or undirected graph. Okay, it doesn't matter as long as the wedges has the weight. Okay, if the weight, the C is all 1, and then this diagram will be exactly like the breadth search. Okay? Yeah? Okay, make sense? Okay, we'll talk about that in the next few days. Okay, that's it for today. Bye bye.